you are listening from, I am pleased to welcome you, all of our Zoom and Facebook viewers, to the 11th webinar of the Mexican Institute of Water Technology, Espacio del Conocimiento en Línea webinar series. My name is Mauricio and I will be your host today. Our speaker is Christian Massari, and he will talk about the added value of satellite observations for modeling and monitoring floods and droughts, insights, and open issues. If you have any questions during the presentation, please type them on the Zoom's chat room, or if you're watching from Facebook Live, please do so on the comment box. We will try to answer as many as possible on the QA session afterwards. All webinars are recorded and available on our social media shown on your screen, so please follow us. Now, I would like to introduce you to Agustin Breña, head of the Hydrology Department. He will read a brief bio and introduce our speaker. Go ahead, Agustin.
Hi, good morning, everyone. Today, like Mauricio said, we have Dr. Christian Massari from the IRPI, from the National Research Council from Italy. He's giving a talk about how to use or how to best use satellite data sets of soil moisture. I will give a short bio of Dr. Massari before he starts his presentation. Christian Massari received his master's degree in environmental engineering in 2008, and then his PhD in hydraulic engineering from the University of Perugia in 2011. Since 2017, he's a permanent research scientist at the Research Institute for Hydrological Protection from the National Research Council in Italy, where he has been conducting research in the field of hydraulic and hydrology, and has developed works in these areas, producing important contributions in peer-reviewed hydrologic and hydraulic journals. His research interests include hydrological and unsurface water balance modeling, development of land data assimilation systems to ingest remote sensing retrievals, microwave and radar remote sensing of soil moisture and precipitation, supply pipe system diagnosis for the reduction of energy and wastewater, floods and drought hazards assessment through remote sensing information and food security. He actively participates as principal investigator and co-principal investigator to several research projects. In particular, he has been principal investigator of SMOS Rainfall 2 project, the WACMOS irrigation project, Stream and Irrigation Plus project by the European, funded by the European Space Agency. And he has actively participated to the project Climate Change Initiative Soil Moisture by the same agency. He has been author and co-author of more than 50 journals, of more than 50 papers in peer-reviewed journals and 21 papers in peer-reviewed conference proceedings and book chapters. So far he has more than 1,600 citations, and he has an age index of 25. He has held more than 50 presentations at conference and workshops with 3 as an invited speaker. He's being a referee for more than 13 international journals and is part of the editorial board of Journal of Hydrology and Remote Sensing. He's a member of the American Geophysical Union, the technical committee, in the Technical Committee of Precipitation, also a member from the Italian Hydrological Society, as well as the European Geosciences Union. So please, Dr. Massari, we are keen to hear, to listen to your presentation. Go ahead.
Yeah, thanks a lot, Agustin, for your introduction. And I think I will share my screen now. Okay. And you should be able to see my monitor, right? Okay. And so thanks again for this invitation. I am very happy to share my research interest. This is part of this is only one part of my research interest, but I think lots of materials. So I think there will be space for questions and interest, also in collaboration if you want. And I take the opportunity to thank all my colleagues that participated in this research, those of my office from CNR and other people around the world. And so this, this is a brief outline of what I'm presenting today, and I will talk about catchment initial conditions and specifically which variable modulates the response of the basin to precipitation. And I will talk about satellite data simulation of soil moisture, rainfall, and a little bit of snow, and the potential ways, limitations, and problems in data simulation into hydrological models. And also I will deserve a last part to the drought, and specifically to how satellite observation in the specific soil moisture can be used for monitoring drought and understanding the crop yield and food security problems. My talk is pretty general, but of course, any topic you are interested, I am available also via email and any other. I'm in the social media, so you can contact me for any further question that arise even after this presentation. And I assume some concept known, but anyway, I will try to be as simple as possible to present all the topics. So for whom cannot understand some concept, I can clarify also later. So let's start with the catchment initial condition and about the variable that modulated the response of the basin to precipitation. I would like to start with this slide, which actually I showed lots of time in my talk, but I think is very effective. And these are two flood events, and in red you can see the observed discharge, and for the first event and the second one, and they have two rather different rainfall accumulations which have generated these events. The first one is 35 millimeters, the second one is 85. So in principle, one could believe that the second one should provide a larger peak discharge, a larger volumes. But what we observe actually is that the first one is 900 cubic meter per second. The second one is much lower; it's 700 cubic meter per second. And so the answer of this it appears weird, this behavior, but actually there is some specific variable that can control the response of the catchment to the rainfall event. So and this is called the wetness condition of the catchment. So it comprehends all the water stored into the catchment prior to flood event. Here, let me explain a little bit better. I just make a simplification here. This is a flood event in black. This is the observed soil moisture in the catchment. This is the precipitation. So the question if there are some variables, that can explain the wetness condition of the catchments before the flood event. One of them is the classical runoff coefficient, which is studied, all of them study under the course of hydrology course, which is the ratio between the, let's say, the direct runoff and the precipitation fallen. And also another one can be obtained by manipulation of the number method equations, and this is called soil water deficit. The larger is this coefficient, the drier is the catchment prior to the flood event. But of course, these two indexes are a posteriori estimate of the wetness condition of the catchment. So actually they are useless because we can know them only after the flood event has occurred. So the question here is there any other variable that can predict this wetness condition, so predict these two coefficients, one of them? So that the classical use of the, we know everybody, the antecedent precipitation index, which is the rainfall fallen in the last 5 days. Basically, this index is a proxy of the runoff coefficient or the coefficient S, but we actually don't know how much better it can describe these two coefficients. So there are also other ones like soil moisture before the flood event or river discharge before the flood event. So we know that once we know these variables, these are very important because they allow basically to help in flood forecasting. So if I know that soil moisture is is a good predictor of the runoff coefficient, basically I know the response of the catchment to the precipitation input. This is a study taken from Tremblay et al., which I'm not co-author, but I think is very useful to understand it. And we extract the water deficit of the soil S from 16 flood events. And we related the S to the predictor that I showed you before, that is the river discharge, the API file, and soil moisture taken from a model. And you can see that there is a linear relationship between the variable and the variable, the predictor that explain better the variance of these points is basically the soil moisture in this case. I think this is very important. And for example, in an area like Morocco, which is basically a scarce data region, it is very important to know soil moisture. But if we don't have stations, rain gauges for temperature, rain gauges for rainfall, and so on, we cannot model soil moisture. So we should find other variables or other source of information of soil moisture. This is a study that actually is still was invited presentation at IGARS, next IGARS, which will be take online in 20 days. And me and a colleague of mine, we explored the relation between the runoff coefficient and the different variables, which are the CCI soil moisture. I don't know, for the people who are not familiar with it, it is basically a combination of multiple satellite soil moisture observations from passive and active sensors. And so it's basically a more complete and more long record of satellite soil moisture existence in the literature. And also we consider river discharge and API 5. What we found is basically that CCI soil moisture is the variable that more correlated in terms of Spearman correlation with the runoff coefficient. So we can explain much of the variables of the flood event extracted from 80 under 81 basins. So lots of basins. All these points represent the catchments. You can see here they are plotted in terms of what is called mutual information, which is similar to a correlation, but is basically is a non-parametric version of it, and is done for non-Gaussian variables. And I plotted the variable here, which has more mutual information with a runoff coefficient. You can see that the blue dots basically almost everywhere in the Mediterranean regions, but there are also other regions where river discharge and API 5 actually have a role, and that they have more information than soil moisture. Specifically in the North UK, you can see some place in the Alps, and this actually is expected that soil moisture, and specifically satellite soil moisture, it doesn't perform very well over very mountainous regions and cold areas. So this makes us understand that soil moisture is very important, but there are also other variables that play a significant role. And in order to build the forecasting system, the knowledge of this variable is fundamental. This is an example of the application of this knowledge to a simple case study in Morocco. And what we found here, we modified each HMS model, which is based on curve number. And instead of using the classical procedure of the SES curve number method for calculating S, we actually calculated with the different predictor of soil moisture from a backend model, from ERA5, from ASCAT, SMOS, SMOS-IC, and SSCCI. And we reproduce the flood event. I think there are 10 flood events. And the blue line here is the observations. The other lines refer to the specific S. And so each HMS model calculated with these products. And what we found is I just reported 3 of them, one from in situ soil moisture, as calculated from in situ soil moisture, as calculated for SMOS-IC, which are a little bit different version of SMOS, but it's based on the same sensor, of course, but it has a different type of retrieval. And also, we use ERA5, which is the most recent reanalysis of the CNWF. What we found that we obtained an agreement with observer discharge, which is best for SMOS-IC, meaning that satellite soil moisture observation can be very useful in case we don't have any information on, for example, temperature, evapotranspiration, so on, for running a continuous hydrological model. But we can do better probably for people that attended the seminar of Luca, this slide, they probably saw this slide already. But so we can do better in the sense that we can embed a relationship between S in soil moisture directly inside the model and parameterize this equation, this relationship, and so as to build a very simple model which uses any sorts of soil moisture. It calculates S from this linear relationship and calculate the rainfall excess using precipitation, and also do the routing through the outlet of the catchment. We published this paper in 2014 on the Hydrology in Earth System Science Journal. And I mean, in terms of operational point of view, this is very advantageous in the sense that we don't need continuous rainfall amount aspiration data sets. So it's very good in poorly gauged area. And also the model is very simple. But this, I mean, make understand, bring at the limits the concept of data assimilation. Is it basically a direct insertion for people who are more familiar with data assimilation procedure? Anyway, we tested the model in many areas. Greece, in Italy, for example, we tested on 35 catchments. These are the results obtained in terms of Sutcliffe. You can see that each dot represents a catchment. The redder the color, the better the performance. And we used two predictors, two soil moisture, one based on the assimilation of ASCAT in the land surface model of a CNWF, and another one is ASCAT itself. And what we obtain is performance in terms of Nash Sutcliffe from median Nash Sutcliffe, very similar each other with a continuous hydrological model, 12 parameters, 0.66, and the other two with a simplified model, 0.6, so very close each other, although the simplicity of the model is much higher for the simplified model. This can be also jumped. This is just an idea of the results that we obtained for Po River, which is the largest river in Italy. And in gray, we have discharge observations, and the different lines refer to the different model simulations for the same configurations I just told you before. We try also to bring to a limit this concept, including, so we include in order to evaluate the surface runoff everywhere, and not just specifically for flood events, we tested this configuration to calculate the surface runoff everywhere, and we use the GPM emission rainfall, the iMerge early run product, and also we use a SMAP as a predictor, and cup number from Landsat lane cover to just have an idea of just to scale the soil moisture based on also the lane cover. And what we obtain is this figure here in the top, and with that we compare its climatology with a more complex model, which is called water gap by Dole et al. In 2013. And just to have an idea if at least the climatology that could be obtained is similar, and actually the results were very encouraging, but the estimates were only referred to surface runoff. And then we submit a proposal with my colleagues, Stefania Camici and Luca, to the ESA, and which wanted to use GRACE plus satellite soil moisture and to predict the total runoff everywhere. And the project is still ongoing, and probably you will see soon some published results, hopefully. And I mean, this is for this part, so you can realize that the satellite information are very useful, can be very useful. They are more accurate than in the past, and they just allow to obtain very good results comparable to the ones that can be obtained with very complex model, although there are also limitations. And this is the topic of the next section, which is the use of the different satellite observations for improving discharge simulation via data assimilation into hydrological models. So for who are not familiar with data simulation, I can say that from one side we have models, and models are inherently uncertain because they are precise and accurate where they are calibrated, but in the sections where they are not calibrated, probably they're very uncertain, and I show you then where. And also they have uncertainty in the parameters, in the forcing. I mean, the rainfall is often contain errors, and this error propagates through the model and through the discharge simulation. From the other side, we had observations, and the ground-based observation are very useful, but they are point-based most of the times. Like you can imagine rain gauge, which is placed in a place, and it should representative of a very small area, while, for example, in Africa, we have rain gauges which are one rain gauge per 100,000 kilometers square or even more. So how much this rain gauge is representative of those areas actually is unknown, and there are lots of uncertainties. Then we have remote sensing, which offer comprehensive measurements of different hydrological compartments. When we now can measure snow, we can measure rainfall, we can measure soil moisture, but actually the information is provided is not really complete. For example, for satellite soil moisture, they can observe only a few centimeters of the soil, meaning that I just lost the root zone part, which is in most of the cases, is the most responsible part for runoff generation. So, and then it comes up with the data simulation. The data simulation basically merge the models and observations, and with the sake of providing a more accurate level that cannot be obtained individually by the observations and models. How to integrate model observations? I mean, there are many filters that have developed in the literature, and you can maybe you already heard about variational data simulation, sequential data simulation, but the simplest way we can do it is this simple weighted average. I mean, is model soil moisture, and if you just expand this equation, you would say that you have a coefficient for soil moisture that multiplies soil moisture from model, and a coefficient that multiplies soil moisture for satellites or ground observation. So when this G is equal to 0, we trust completely into the model. When G is equal to 1, we trust in the satellite observation or observation. And so every sequential technique is an evolution of this simple equation. I mean, that you can heard about ensemble Kalman filter, particle filter. Particle filter is a bit different, but anyway, the concept is this. I mean, it's a combination of the two. In addition, we have to say that when we merge information from satellite soil moisture and models, they speak different language very often. And specifically for a conceptual model that the heavy hydrologist is often uses, and that the information of soil moisture can be different. They provide a level of the reservoir which is a proxy of the soil moisture. So it's not the same quantity in most of the cases. Also, they have different spatial resolution. And as I said before, there's a different vertical support. Also, they are characterized as different climatology. And so they are biased each other. So we cannot ingest directly satellite observation into models. We have to deal with them a little bit, correct the bias, understanding which layer to ingest the observation, and so on. But why is it important to correct the state? I mean, the soil moisture is a state of the system. Why is it important to merge this information with an observation? Because if I improve my model state, for example, soil moisture, I can improve the representation of the pressure condition that I told you before, and thus I can improve runoff. This is the basic idea of the data assimilation, for example, of soil moisture into hydrological models. There have been many studies and so far, and all of them provide some examples, and there are, I think, they are a bit controversial because they don't. I mean, they show that there could be a potential improvement. I mean, some of them show clearly an improvement, but there are also other things, other limitations, or for example, some studies improve the high flows and deteriorate the low flows and so on. So the results are not so clear. I mean, it's not said that if I simulate satellite soil moisture observation to a model, the results are better. Why? Because there are many issues that can impact the results, like the impact of the season, the model structure. For example, there could be a missing link between the surface layer models and root zone parts. And then if I can assimilate any satellite soil moisture, but this soil moisture actually doesn't affect the deeper layers of the model. And so if my runoff is generated by the root zone part, I don't obtain any improvement. Also, there can be many bias correction procedures, and some of them are more optimal, some of them are less. And also there is an impact of the filter assumptions and impact of the climate and the hydrology of the catchments. If in my catchment there is always snow, for example, and the flood generation can be generated by rain or snow, or can be generated by melting, so the soil moisture actually, it doesn't have an effect on the improvement. And also there is an impact of the catchment size and other things. So for describing this, we published a paper in 2015. Of course, we didn't take into account all these issues because I think it's almost impossible. But we saw the data assimilation like a complex recipe where we have different ingredients and different cooking techniques where we manipulate and mix in these ingredients. So we can have different bias correction, and we have different way to represent the model error, to calculate the observation error, and so on. But we start to look at some of these issues already on 2015 on this paper in remote sensing. And we focus, of course, in a place where we live because we know better the situation there. And we use a simple model, one layer, and we assimilate a scatterometer, soil moisture-based scatterometer data. And also we assimilate, we use ensemble common filter, which is an evolution of the equation simply that I showed you before. And this helps to weigh in a optimal way the observation error and the model error. And also we use 5 catchments with area ranging from 140 kilometers square to 2000. And we focus on rescaling techniques. So we have to just match the satellite observer, so make understandable the satellite observation with a model. If we try to understand the impact on low and high flows, also the impact of the season and impact of the other things. For example, we found that if we can obtain an improvement in high flows, but this doesn't necessarily mean that for low flows we have an improvement. So this plot shows basically this. Each of this group refer to a catchment. Each bar refer to a rescaling technique. If you just neglect this for now, but you can see that if I am above, I'm improving the open loop, meaning that the data assimilation provide better results than the results without data assimilation. When I'm below this graph, I obtain deterioration. So you can see that it's a bit up and down, and for low flows. For high flows is actually mostly always true that I improve, but you can see that, for example, in some specific case, I obtain deterioration, and in other I obtain improvements. Also, we were interested in the impact of the season. You know, maybe you're in Mexico, so the climate is very different. But in Italy, the spring and autumn are the season where the soil moisture is more variable. I mean, the temporal variation of soil moisture is very high because we have rain, we have sun, and so dry, wet, and this makes the soil moisture signal very variable. And also we want to understand, I mean, if this has an impact on, or the data assimilation is impacted by this behavioral soil moisture. And we plot this graph. On the top, we have deterioration. In this case, it's the opposite of the graphs I showed you before. At the bottom, I have improvement. This is basically a simple random mean of the normalized room square error, which is basically a ratio between the room square error with assimilation of soil moisture and room square error without assimilation of soil moisture. If it's larger than 1, I'm deteriorating and I'm in this part. If less than 1, I'm improving this part. This gray area refer to the variability of soil moisture, to the soil moisture variance. So during the winter and autumn and spring is much variable. During the summer tend to be very low and steady, because in the summer it's very dry in Italy, generally, not like this June, because it rained a lot. But anyway, what we found is that the higher variability generally corresponds to improvement. I mean, this means that the initial conditions, I mean, regulate of the soil moisture regulates the response of the catchment, and this is particularly true in periods with high variability. And this is an important result also to optimize the data assimilation system, because I can prefer to assimilate soil moisture only in the spring and just neglect the assimilation in the summer. And for example, in the summer I could assimilate discharge, so on. So to understand better all these topics, we run an experiment with a lots of catchment like before. They are almost the same. And we used, in this case, almost 800 catchments across Europe with very area ranging from a smaller one, 150 kilometers square, to more than 10,000. And we use, in this case, a two-layer model. And we assimilate CCI products, both the active, passive, and combined products. The active contain only scattorometer observation, that which allow to calculate the soil moisture, and the passive one contain only passive radiometer, like SMOS, SMAP. In this case, SMAP is not included in the product, probably. I don't know if it will be included in the future, but anyway, you can use SMAP, AMS3, and AMS3-2, and so on. And also there is a combination of these two products. So we wanted to explore all of them to understand any impact of, for example, vegetation, of topography, of the starting performance of the model, which has this one. And you can see in red, you can see the dots. Each dot is a catchment, and which refer to the outlet section. Of course, there is a a boundary that you cannot see here because it was too messy, the vehicle otherwise. But anyway, you can see the red dots are the ones that where the model performance are best, and the blue dots are the ones where the model performance is less optimal. I would say they are always larger than 0.5 in any case. And we use KG score, which is a score that ranges from -infinity to 1. And which is composed by a correlation coefficient and variability coefficient and bias. It is basically like Nash-Sutcliffe, but it optimized this parameter here. And when you use for calibration, this is much better than Nash-Sutcliffe. This paper is submitted to Water Research, and hopefully we will have positive feedback from the reviewers. Here are some results that we obtained. For example, we obtained negative effect of data assimilation during the cold season, a little bit different from what we obtained from Tiber River, but because we explore, I trusted more these results because we explore so many catchments that we can say something more in this case. And also we only focus on a very cold season that for the Northern Europe can be, the soil moisture can be very steady. It's always wet there. But in fact, we obtained some improvement in Spain and the Mediterranean area. And also we have a more positive impact during the warm season and almost everywhere, except in the northern latitudes, which is obvious because, we have a snow melt here. And also we try to understand also the beneficial impact of the assimilation in terms of this is the original model simulation, which we call the open loop. And this is the improvement. We have more improvements when the model performance are poorer. And we obtained a little bit different results for low flows, but I'm not talking about here. This is another one, another study which is published in the Journal of Hydrology, and where we assimilated Sentinel Wireless map into SWOT hydrological model, and we use this product is not really Sentinel one, it's Sentinel plus OSCAT, which has a 1 kilometer spatial resolution, and we consider two small catchments. There is one that is more vegetated than the other one, but both of them are less than 100 kilometers square. And we use a 2D ensemble Kalman filter in this case, another evolution of the equation I showed you before, which also does the data assimilation also in space and also in space. Incorrect for closer pixel based on observation at one location. Also, we used triple collocation, which is a technique to calculate the observation errors, because I didn't say very well this, but we need techniques to calculate the observation error. For example, if I have lots of stations at the ground, I can compare the satellite with an in situ station soil moisture to evaluate the errors, and then I can use that error. But there are also techniques that have been implemented to calculate this observation error without knowing anything about the in situ stations. And what we found is that the performance of the active sensor is better in the less vegetated catchment. And for example, the passive sensor, which is MAP, is better in the more vegetated catchment. We don't know exactly if there are other reasons, so we try to explore many things, but we found this. But the notable results also that I showed you before is is that both SMAP and ASCAT have different temporal resolution, different revisit time. Basically, as we have SMAP in Italy every 3 days, we have ASCAT almost 1.5 observations per day. Now with the launch of other satellites with more observations. And so ASCAT are much higher temporal resolution than SMAP. And so we want to explore if this impacted data assimilation results. This is the percentage of improvement in terms of Nash-Sutcliffe, in terms of the room square error. And for doing that, we run the data simulation with ASCAT at full resolution with SMAP. And then we downsampled ASCAT. I mean, we take only some observation from the full ASCAT, the one closer to the one of SMAP. So when we have a passage of SMAP, we took some ASCAT observation. So they are basically this ASCAT downsampled. It has the same temporal resolution of SMAP. So what we found is that if we downsample ASCAT, we have less performance than at full resolution, meaning that the temporal resolution is has an impact on the data simulation. And in this case, where we use Sentinel-1 and ASCAT for having a much higher spatial resolution than ASCAT, because it's 1 kilometer versus more or less 25. In that case, the temporal resolution, in this case, the temporal resolution is much more important than the spatial resolution. Of course, this is just a case, and to understand if it is true, we should run an experiment for many, many catchments as the one I showed you before. But it's a first result. I mean, it's just to put them here and to understand the potential detrimental impact of the resolution and so on. But there are other ways also that we use satellite soil moisture for improving flood modeling. This is indeed soil moisture contain information about the rainfall. You can see here that these two figures on the top is the after a rainfall. I have those purple and red parts which are wetter, and if 12 hours passes and I still have some trace of the signal, so it means there is some persistence at the ground about the rainfall. It can be used to calculate to have information on rainfall. This is also another example. It's a land surface model run with a satellite rainfall data set. I think it was CMORPH. And you can see that this is the satellite soil moisture, not the satellite soil, the soil moisture of the model at the ground. And you can see that on the other side there is moss, and you can see that the spatial difference are very high, meaning that probably the rainfall area to force the model is not very accurate, and the model and the satellite here actually has a much different behavior. So this means that satellite soil moisture contains valuable information about rainfall. So how to exploit it? Probably you already see this yesterday. This is basically a simple water balance equation that we study at the university, but even before, that is inverted for soil moisture. And for that, is inverted for precipitation. So you have a relative saturation here, precipitation, surface runoff, evapotranspiration, drainage. With some assumptions, we come up with the precipitation as a function of the other variables. Then there are many versions of this equation. So if you're interested, you can just read the publication of Luca Brocca. But there are also other methods to retrieve information of rainfall from soil moisture. This is another method which is called PRISM, and which exploits the differences between the satellite soil moisture measurements and the simulated soil moisture using a satellite product. If I have this rainfall in red, I can obtain with a simple model, with simple hydrological model, this soil moisture here. And if I have a moss here, observations, the red square, I see that the simulation is far away from the observations. If I multiply by a factor the precipitation, I mean a random factor, I can take different rainfall. You can see how it varies, the green one, and as a result, I obtain different simulation. So what I'm done here is taken the simulation in gray closer to the observation as moss. And this actually allows to correct the precipitation, which is the one in blue, which have produced the small soil moisture. This method was developed by Thierry Pellerin, and then was applied by many other researchers. in a small rainfall project, where also I'm co-author of this paper with these guys. And this the evolution, this MOS plus rainfall project actually allow to provide an improved data set. So we merge, in this case, iMerge product from GPM with multiple satellite soil moisture observations in using both SM terrain and the PRISM approach. And we have a data set ready that you can use and download, available now from 2007 to 2019 and all over the world. And you can download the data set here if you're interested to use it. We also tested this data set in Africa, specifically in Africa, and we found that we obtained performance similar to a rainfall from ERA 5, GPCC in iMerge, Final Run, but also in Europe. And so the data sets actually, at least for this catchment that we tested, works relatively well. And we are satisfied, we're really satisfied. We also want to do test which is better to go to use SoilMaster for rainfall correction or for in a classical data simulation with state correction. And this is another study published in Remote Sensing. And what we found is that for high flows, the rainfall correction seems much better than the classical data simulation schemes based on ensemble Kalman filter. And this is basically in line with other studies on the topic. But for low flows, there is some, so the rainfall correction seems not so performant. And then, I mean, so here we have another thing that we should explore further and probably combine the two if there is a theoretically a way to do it. And so something still ongoing. And also we didn't do only satellite soil moisture assimilation. We are now moving to snow data simulation. And we started with Danube River, and this is only the first results where we calibrated model and we tested some products over there. But the research question we wanted to answer here is, can satellite or snow and soil moisture data simulation help to improve the model efficiency on intersection? Because, for example, in this case, I calibrate the model on this here, and here the key G value is pretty good with 0.81 using trim observation as a rainfall. But if I go to the inner stations, and you can see that the stations below, you can see that the performance are suboptimal. So the idea of assimilating snow and soil moisture inside the catchment is to provide a more consistent results and more physically sound with respect to the one I obtain here. Because I'm sure that if I can estimate soil moisture here from the model, I can compare with some in situ stations. The results would be not very good, because the physics of the model actually lacks a little bit due to the calibration in the final section. This is another topic. Actually, floods and droughts are very well connected, and we have also studies now ongoing on the relation between drought and floods. But in this case, I will present you just a simple way that show that satellite observation, in particular soil moisture, contains useful information for agricultural applications and for crop yield. I think everybody knows what is a drought, although the concept of drought is a bit vague, but we know that there is a period of below average precipitation in a given region, and which results in prolonged shortage in water supply and surface water, groundwater, and so on. So the concept of drought is very dynamical. Also, it can last from few weeks, when we call a meteorological drought, to several years when we call hydrological droughts. And specifically for agriculture, what is important is the agricultural drought, which scale of about 3 months. And why so important agricultural drought? Because it has an impact on the crop yield, and we know that the food is the next challenge for the future. So, and if we will have in the future more drought events, more severe drought events, would be this means less food for the humanity. And we can this is a nice picture of Les Ketal from Nature. We show that when there is a drought, the failure in crop production is much larger for data-rich regions and very wealthy regions like Europe and North America. Why? Because in these regions, the crop actually production is maximized. I mean, everything is put in at the best for the profit. And while in regions like Asia and Africa, people most likely they don't have the means to do agriculture in such a way. So when we have when we miss the most important thing for a crop, the water, the crop failure is much larger in these regions. But also is important also in other regions. So we have to explore this. And how to characterize drought? I mean, there have been lots of indices that try to describe the drought. This paper of Zargar et al. Counts 74 of them from 1993 to 2014. And the simplest one, probably all of you know them. Are based on the concept of anomaly. So we seek the deviation with respect to the past of an observed variable that can be precipitation, for example, and we normalize it by standard deviation. And we use fitting, statistical distribution fitting to fit the data and a representation of the drought in a more homogeneous way. So there were being developed standardized precipitation index, standardized soil moisture index. All of them are basically anomalies, homogenized to have a better representation in space. But all of them require long-term data records. And this is a problem. I mean, this is a problem for soil moisture. For rainfall, the distribution of rainfall around the world, I mean, it's not bad, at least in the most populated regions where we have crops. But in Africa, for example, we have some data many rain gauges that actually are very far away each other. Also here in Amazon. But for rainfall, I mean, we are pretty okay with the drought. But for soil moisture, for in situ soil moisture, actually, these are the station taken from the International Soil Moisture Network. And you can see that the distribution of the station is rather different from the one of the rain gauges. And so this is why we want to encourage the use of satellite soil moisture observations. And for example, the CCI soil moisture that I just presented, maybe too late here, but it emerged different active product, passive products, and different active products to provide a product which is available from 1980 to 2020. So this product can be used basically for building an index, a drought index. So what we have done here is this, which everything is published in this paper of Sara Modanesi at Tani Water Research. And we wanted to understand if satellite-based soil moisture indices are appropriate for monitoring agricultural drought. And we wanted to know how they performed with respect to land surface model, because basically now the monitoring, because of the length of the record required, the monitoring with the drought index built with soil moisture is basically based in with model. And also we wanted to test how the satellite soil moisture performs with respect to a precipitation-based index, and which is the standardized precipitation index with accumulation of 3 months. The 3-month scale is basically the scale suggested for the calculation of SPI for agriculture. So we explored this. I mean, we did a study in the two regions of India known as Maharashtra and Karnataka states, and these two regions have seen recently very severe drought events with actually determine also migrations and many problems. So these two regions are very important. And we calculate the SPI3 with ground-based station from International Meteorological Department of India. And we use 18 years of crops, and also we calculate the satellite soil moisture index, drought index with ESA CCI, so a satellite soil moisture product with a model, a reanalysis called MERA2. And we focus on maize and wheat. And this is the previous analysis to understand which month is more sensitive to the so for which month we have to understand the drought. For example, for wheat, November is important. For maize, another month is July, August, and September. So that the missing of water in these months is particularly important. And then we try to relate the drought indices to the crop yield. What we found is for maize, this is for satellite, this is for model, and this is for precipitation. And this is the correlation obtained. All these points refer to the year of production and the specific drought indices obtained in that year for that specific month. Basically, the difference here are that this is maize is rain-fed, and you can see that satellite soil moisture is much more informative than the other two, but not much about the rainfall because it's rain-fed. And when we move to winter for wheat, we basically have that the most sensitive variable to the crop yield is again the CCI soil moisture, and we have deficiencies of the other two. This could be, we didn't test, so this can be only speculation, but this could be also that this crops is irrigated, so the satellite can somehow have more information if there is an anthropogenic impact on the soil, meaning that people are irrigating. And this is all of the material. And if you have questions, I'm happy to help. And this is also my mail and my web, my page on the web where you can actually take a look if you're interested.
Thank you very much, Christian, for such an interesting talk. While people finish typing their questions, I'd like to give some announcements. So I'm going to share my screen.
Okay, I stopped sharing, right?
I don't think so, but I think I can share mine.
Okay.
So I'd like to remind you that you can watch this webinar and every webinar on our social media, so please make sure to follow us. And also I'd like to announce our next webinars. Tomorrow we'll have Angelica Tarpanelli talking about multi-mission satellite observations for river discharge estimation at 10 a.m. in Mexico City and 17 hours in Italy. And also we will have our regular Friday webinar. Our next guest will be Jacqueline Fortin with Deep Learning para asistir en la predicción de incendios forestales. This will be as regular in Spanish for our Friday webinars. So now let's go with the questions.
Okay, can I?
So, yeah, go ahead.
Yeah, I can read the question and answer, right?
I will read the questions for you.
Okay, perfect.
If that's okay. Yeah, so Shahir is asking, how did you incorporate snow melt and glacier melt in your modeling approach?
I think which one, the simplest one, actually, that one was just For the specific case studies, like for example, Morocco, we make sure that we didn't have snow, but we use a simple temperature degree model in some cases, which I didn't mention. And because the idea was to maintain the model as simple as possible. And also the global runoff simulation part, was just a simplification of everything. And in the project we are running, we are using some more much better model like temperature degree to maintain the model simple. Or in the model I'm using now, with which is a Sacramento model, I'm using Snow 17. I don't know if this answers the question.
All right, thank you. Now from Jackie 14, have you performed a similar exploration with soil type instead of land cover?
Not yet. It would be very interesting. Of course, the soil type was an influence in the as an influence on the runoff generation, can have a great influence. In addition, also to topography, which actually overlooked so far. This was only to try to understand if a model simple in that way could provide reasonable results and could provide information also for data simulation.
Right. Now, Agustin has a couple of questions. So the first one, how much error did you find using triple collocation technique? And did you use them only for stream flow gauges?
I used the triple collocation for calculating the error in satellite soil moisture observations. And I mean, if the assumptions of the model hold, the technique is very reliable and very useful. In addition, I mean, a combination of the combination of the equations of triple collocation allow to correct the bias between among the data set that you're using to calculate the error. I never used the technique for river discharge, but I used them for rainfall, for calculating the error of rainfall. I have a paper published in Hydrology and Energy System Science in 2017 that you can look at it, and it can answer you some questions.
Right. He's also asking, based on your findings, do you recommend using this technique in developing countries with limited observations and only for stream flow or also for rainfall?
Yeah, you can use it for rainfall because we tested, but we tested only on some time scales like daily and 25 kilometers and a little bit smaller. We never test with hourly observations. We never test with specific rain gauges. So I cannot answer about those, but I can answer about using in satellite and I mean like much larger scale.
All right. Now Bramha is asking. I'm sorry if I pronounced the names incorrectly. So Bramha is asking. Grace shows positive TWS anomaly in Maharashtra and Karnataka in the last few years. Why do you think it tells a different story?
I don't know if Grace shows specifically in that area positive anomalies. Of course, Grace contains information of soil moisture, but also groundwater. As far as I know, the northern part of India, the groundwater exploitation is very high, but in the states we analyzed, actually the groundwater part is much less, and so we relied on soil moisture in this case. Probably for the complete analysis, we should consider total water storage anomalies from Grace also in these areas. So the different compartment actually can have a different effect, I think.
Okay, our next question is, you showed that soil moisture is highly correlated with runoff. I guess this was in fear for Europe. How about Asia and Africa, where groundwater irrigation is not controlled? Therefore, do you reckon this correlation will drop for such regions?
It can be, especially in very convective type of areas, where also there are many large rivers. the impact of soil moisture can be of course less, and specifically at the end of the season when the soil is almost wet, and of the monsoon season. But I've never explored, and I think this is something missing because of the lack of many discharge, level of the river stations.
Thank you very much. Our next question from Romy. Did you check how reliable is SM2 rain in Latin America?
So say again, sorry.
Yeah, did you check how reliable is SM2 rain in Latin America?
We checked and we found that over semi-arid areas, it works very well, and specifically in areas where satellite rainfall have the problem of droplets of evaporation before. So they basically state-of-the-art satellite rainfall products estimate rainfall on the clouds. When there is rain, these drops actually can evaporate it. And since SM2 rain is based on soil moisture, it can provide a better representation of the rainfall that actually touch the land. But for semi-arid areas, like for example, Eastern Brazil, some parts of Mexico, the product works very well, much better than the other rainfall products. Of course, if I move to the forests, the product doesn't work so well, and the idea of the merging of the GPM with SM2 rain was due to this reason.
Okay, thank you. Our next question from Hassan Omar is, how does soil moisture behave in high terrain area? And can we use satellite soil moisture in high altitude area and then use this for rainfall runoff modeling?
Yeah, that's one of the problem of satellite soil moisture. First, because the very high areas are generally more complex, and there is, for example, forest there. And so the quality of the satellite soil moisture observation can be very low there. And also because of the impact of snow and snow melt. So I wouldn't at first recommend the use of satellite soil moisture in very mountainous areas like Rocky Mountains, Andes, but everything must be checked, of course, because there might be some areas where there is still information from the signal.
Okay, some people is asking to share the slides, so I like to remind you that this webinar and every webinar will be available on our social media, so please follow us and you will be able to watch this webinar there. So Juan Carlos is asking, based on your experience, is it better to use multivariate indexes to characterize drought or univariate indexes could be good enough?
I think it depends on the goal of your analysis, but I think multivariate indexes are much better because they provide a clear picture of what's happening there from a different point of view. And so I fully agree that using multivariate index is better.
Okay, thank you. And the next question from Saul Arciniega. Is soil moisture assimilation better than a multi-objective optimization using discharge and soil moisture to improve hydrological simulation?
Even the multi-objective optimization using different variable like soil moisture or even evapotranspiration can be considered a data simulation. So the classical data simulation, the way I describe it, actually can be better, but maybe if you use satellites, maybe probably is better in the sense that they can weigh in an optimal way how much satellite information I want to bring to the model. When I do multi-objective optimization, somehow I can do that. And for example, variational data simulation technique are very similar to it. And so it can also depend on the process you're considering, but the multi-objective optimization relies also on the availability of many in situ stations for river discharge or soil moisture, you can consider also satellite there, of course. It can, there's not clear answer to this question. Actually, it depends.
Thank you very much, Christian. I think those were all our questions. So we'll go now with Agustin for a final statement of this webinar. Go ahead, Agustin.
Yes, thank you, Mauricio. Actually, I think you missed a question that I did, so I will read it.
Oh, I'm sorry. Go ahead.
So about in your last slides, when you show the results of your drought study, so when you're basically using statistics from these soil moisture data sets from the satellite to generate the standardized drought indexes, yeah. Right? Have you considered to generate a new index that does not rely on statistics? For instance, if you know the soil properties of the pixel that you're analyzing, and you know the field capacity of the soil of that pixel and the wilting point, and between them you have the available water, and if by using the satellite data, you know, for instance, that in a given month, the value of moisture is closer to the field capacity, then you have enough water. If it's closer to the wilting point, then you probably have water stress. Your crop is experiencing water stress. And is there a way that, I don't know, I'm thinking that you could generate, or develop an index that, or correlate the crop production using this, like a curve or like a linear model between the wilting point and the field, the temporal distribution of your soil moisture based in knowing these two thresholds?
Yeah, this is a good point, and that there are indices also based on this concept. And initially, we also consider one of these indices, but then we try to we try to be homogeneous in the comparison, and we used only statistical type of indices. But of course, you can build it. The only difficulty that I see is to add additional uncertainty, in the sense that you have to know the field capacity and the wilting point, and this is not very straightforward. And there are also functions that can be based on the content of, for example, clay and sand, that can provide you this information. But I think if you have specific studies for that in an area, I would suggest also to use this index. Probably is better. Mm-hmm. And yeah, I mean, it could be done. It could be done.
Yeah. Of course. Okay. Well, thank you. Well, there are no more questions, so I will just wrap up this this talk from Dr. Massari by giving a closing statement about a summary of what he presented today. So his talk consisted about different topics related to soil moisture, the potential of using satellite measurements. Soil moisture measurements from satellites are have a lot of potential. First, he displayed the role of soil moisture deficits in the hydrological response at the catchment scale. Why are these soil moisture deficits important, and how can they be estimated using remote sensing? He showed that hydrological prediction is also possible without using conventional variables such as precipitation or evapotranspiration as inputs in a hydrological model. He showed a very interesting case study where using soil moisture and variation of total water storage from the GRACE mission can improve or can simulate properly hydrology, terrestrial hydrology. And then he also displayed some results related to data assimilation of soil moisture. So this is how to integrate models with observations Of course, there are challenges such as the spatial resolution of the pixel that not always match, do not always have the same resolution. Also, the observational scale, in this case, the vertical depth, can be also an issue. And finally, the model process representation and the structure. This can also lead to different results, so you need to be careful. And well, the conclusion in this issue is that for this topic is that data assimilation can improve hydrological predictions, but in the case of Italy, only at some periods of the year. In this case, in Italy, the results show that mainly during spring and autumn, which is where the variation of soil moisture is higher, the data assimilation can improve the results. So of course that leads to a lot of questions, and that also requires that more research is carried out in other hydroclimatic regimes of the world. There's also then he also showed how soil moisture can be used for generate rainfall maps at the continental scale, and he showed a nice example from Africa. And finally, in the last topic, he explored the potential of using soil moisture for drought and food security purposes. And so far, well, the results are very promising for crop use in rain-fed agriculture systems. So I think overall this was a really compelling presentation, very broad, but at the same time you gave a lot of insights and ideas, so we can carry out similar studies in other regions of the world and using new data sets, and of course also open source models and data sets that you have been using for many years. So again, thank you, Christian, for this insightful presentation, and we will send you your talk will be available on YouTube in the coming days, and we will also send you the list of participants, so in case you have some interest. Okay, so thank you very much, and have a nice evening in Italy, and for those in Mexico, have a nice day.
Nice day. Yeah.
Thank you very much, Agustin. Christian, is there anything else you want to add?
No, I want to just thank you all, the participant, and it was very nice to present this topic. And again, if you have a question, you can write me up, and we're happy to answer. And thanks a lot for this opportunity again, and good luck for the future. And probably we will start some collaboration with someone, and I'm happy. Okay.
All right, thank you very much. That was all for today. So to all our participants, we hope to see you again on our next webinars. Please be safe. Goodbye.
Goodbye.